In this video, I want to look at the definition of what a prime element in an integral domain is and a couple of consequences of that definition. The definition comes right out of number theory and the ring of integers, which of course is an integral domain. But the only difference is we're no longer going to assume that our integral domain has to be the integers. So we're going to let D be any integer. We're going to let D be any integral domain that does have one property. The property that we're going to insist upon is that the multiplicative identity and the additive identity are separate elements. And let me get my subscripts to agree. So the 1 in the domain and the 0 in the domain are not the same thing. I want to let A be any non-zero element, and I also want A to not be a unit inside my domain. We are going to call A a prime element of our domain D if and only if A has the following property. And this property is something that you know from prime numbers. If A divides a product B times C, then either A has to divide B or A has to divide C. It's that simple. And yes, if D is indeed the integers under normal addition and multiplication, then A is prime in number theory is the same thing as A is prime under this new abstract algebra definition. And my handwriting is not being very good here. Now, I do want to kind of look at this definition for just a minute and realize that this stuff looks sort of similar to a definition that we had about ideals not too many videos ago. So at this point, I want to actually recall some stuff from videos quite some while ago. So I want to recall a definition that said this. If I had R is a commutative ring with an identity, and I was an ideal of R with this property, and this property said if a particular product belonged to the ideal, then either the first thing in the product belonged to the ideal, or the second thing belonged to the ideal. If we had that, then we called I a prime ideal of the ring R. Now, we've got the same basic kind of property of something being a product saying that one of the elements inside the product has to behave. And there is a strong connection between these two definitions. The definition that we just introduced about a prime element being if A divides the product, then A has to divide one of the two things. And this old definition about prime ideals, if the product is inside the ideal, then A has to be in the ideal or B has to be in the ideal. Well, what is the connection? Well, it's pretty obvious. And I want to make that quite clear. So what is the connection between these two definitions? Well, in a commutative ring, what I want to realize is that we always have principal ideals. So let's let D be my integral domain. And integral domains, of course, are known to be commutative rings with multiplicative identities and have no zero divisors. I want this integral domain to have the property that 1 and 0 are not the same thing. And I want to let A be any non-zero element. And I do know that I can, and I'm going to go ahead and assume that A is not a unit. And I do know that the principal ideal generated by A, which would look like R times A, where R is running over all of the elements of set D, this is going to be a proper subset of my domain D because A is not a unit. And it's also not going to be equal to the set containing just the 0, since A is not the 0 inside my domain. But I do know that this is a principal domain, and here's the neat thing. We're going to have that this principal ideal generated by A is going to be a prime ideal inside the domain D if and only if, well, let's see, prime ideal says C times D belongs to the ideal implies either the first thing belongs to the ideal or the second thing belongs to the ideal. But let's see, that basically can be translated. This statement here means, well, CD gets inside the principal ideal generated by A if and only if A divides that product. And so this implication says A divides that product if and only, A divides that product implies that A divides C or A divides D, because C inside the domain would mean A divides C, and D inside that ideal means A divides D. I think I said that wrong. So let me say that clearer. CD belongs to A. The principal ideal generated by A means A has to divide CD. And C inside the principal ideal means that A has to divide C. And D inside the principal ideal means that A divides D. So this statement here is just a translation of that statement. Of course, this is the definition, since we've already assumed that A is not a unit and A is not equal to the 0. This says A is a prime element. Inside my domain. In other words, what we've now shown is we have just proved this proposition. If I have a domain, an integral domain, with the property that 1 and 0 are not equal to each other, and I take a non-zero element and a non-unit element, then we know the principal ideal generated by A is a prime ideal inside my domain D if and only if A is a prime element inside my domain. Technically, A as a prime element is going to imply this stuff, and we could get just a little bit more picky here, but I'm not going to worry about that.